Hi, this is the Midland Hotel in Manchester. It's one of the most spectacular hotels in the city. It was built by the Victorians as a railway hotel, and you can see it has quite a distinctive pink colour. The reason for that is the rock it's built of, and that's what I want to look at this lesson. I want us to understand how this rock, which is actually a very famous and very commonly used decorative and building stone, actually came to be. And perhaps to turn on its head some of the things that we've learnt and accepted so far. This particular rock comes from Cumbria, on the eastern edge of the Lake District, a place called Shap. And it's a rock that we call the Shap Granite. You're going to need your A3 Shap Granite worksheet to go along with this video. Okay, let's start by having a look at the Pluton itself. This is a simplified geological map of the area. What I'd like you to do is to work out when this was intruded. Can we work out from the geology of this site the time period that it was formed? Also, when we look at this, what effect does this intrusion had on the country rock around it? Can we pick out maybe two things that have happened as a result? Press pause now and have a go at answering that on your worksheet. Okay, this is a geological map of the wider area, of the whole sort of Lake District area. Shap itself is that Pluton over there. It's not a particularly large Pluton. It's possibly only about 8 square kilometres, but it's one because of its decorative features and because of its clear geology. It's used in buildings, statues, and teaching collections across the country. It's a very distinctive rock. It's about 400 million years old, intruded at the end of the Caledonian orogeny. So we should have seen from the map that it must have come after the Ordovician and Silurian, but before the Devonian, because there's an unconformity of the Devonian rocks cutting across the metamorphic aureole. We see as well that the intrusion of this Pluton has sort of domed up the rocks around it. You can see the dip goes away from the Pluton in all directions. Okay, let's have a look at the rock itself. This is where it's actually quarried. It's called the Shap Pink Quarry. And we can see a rock face there that's dug out. It's not worked all the time, but it is worked for special orders as and when it's needed. Okay, let's have a look at a sample of this rock. This is a specimen of Shap Granite. It's from the granite section of my rockery here in my garden. What I want to do is look closely at this to see if we can describe the rock and try and then understand how it formed. So if we have a look at the rock close up here, you can see that the rock here is made of random interlocking crystals. And particularly if we pour a little bit of water on this, we can really see that this rock has a porphyritic texture.
If we look carefully at the minerals that we find within this, we have some phenocrysts of orthoclase feldspar. If we measure some of these, like that one there, we see it's about 3 centimetres across. These phenocrysts are euhedral in shape and really, really well defined. The ground mass of this rock, you can see, is made up of several different minerals. We have these white minerals in here. These are plagioclase feldspar. We also have the sort of grey coloured mineral here, which is quartz. Both of those crystals are 3 to 5 millimetres across. And then there are smaller dark ferromagnesium minerals, which are biotite. You can see some that are really quite shiny. And we also have some that are a bit more vitreous, that's a possibly hornblende. This rock is like the one we're studying for this lesson. Can you now justify why this rock has been identified as a granite?
Okay, having seen the specimen, what I'd like you to do now is press pause again, and on your worksheet, next to the photograph of the specimen, justify why that rock has been identified as a granite. Okay. We now have an idea of what this rock is like, certainly in terms of its composition and texture. What I'd like to do now is explain how this rock formed. And I'd like you, on the table at the bottom of the left-hand side of your worksheet, to list the minerals in the order in which they crystallised. 1 being the first, 5 being the last. And I'd like you to give reasons for your answer. What was the cooling history of the Shap Granite? Press pause now and have a go at that. Okay, so we should now have a description and a photograph, perhaps that looks something similar to this. We know our rock is coarse-grained, we know it's silicic, we know it's porphyritic, with these 5 different minerals that we find in there. Now, if we look at these minerals and using the size of the crystals to determine the speed at which they're cooled, I suspect most of you, if not all of you, would have come up with an order that looks a bit like this. With orthoclase feldspar as the first mineral to form, followed by plagioclase, quartz, because they're a similar size, and then biotite and hornblende as the finest grain ones that must have filled up the bits that were left. The small gaps and the tiny last bits of magma that existed around the bigger crystals. So we've organised it by decreasing crystal size. So our interpretation of this is likely to be 2 stages of cooling. A slower stage forming the orthoclase feldspar, and then a faster stage where the rest of the minerals crystallise out in fairly quick succession. That would fit in with everything we've learned so far at GCSE and even AS level. But I'm going to throw a spanner in the works. Some of you may have spotted the problem already. think back to Bowen's reaction series. This is a phase diagram. We're going to look at these in a bit more detail in a subsequent lesson. But this graph shows us the temperatures at which these minerals will crystallize at when we have different pressures. So I want you to look at the cooling of the Shap Granite that we think happened at a pressure of about 0.2 gigapascals. I've marked it with the red line on this graph and on the one on your handout. Work out what order these minerals must have formed in. Write those on the table in the middle of the right-hand side of your worksheet. And also, can we work out the crystallization temperatures of each of these minerals at that pressure? See what you can come up with. Press pause now and have a go at that. Okay, let's see what you've come up with. This is the table. And if we look at the order of crystallization as the magma gets cooler, we see that hornblende would crystallize first, followed by plagioclase, followed by biotite, quartz, and finally orthoclase feldspar. If we fill in the temperatures at which this occurs, we see the succession. That fits in with Bowen's reaction series. But if you compare that to the order that you came up with for your first interpretation of this, we see that we have orthoclase followed by plagioclase, quartz, biotite, and hornblende. Yet our second answer, where we use the phase diagram, is pretty much the reverse. How can that be? Which one do you think is the most likely interpretation? Do we go with what we've learnt about crystal size, or do we go with the experimental results from Bowen's? And if we do, how can it be that the last forming mineral is the one that's grown to the greatest size? To answer this, we need some new ideas. What I'd like you to do now is press pause and watch the two additional videos. You'll find links to them about an idea called Ostwald ripening and also how that actually relates to ice cream. Watch those before we come back to the final answer. Okay. We can see that this idea of Ostwald ripening gives us a different way of thinking about the crystallization of magma. But for Ostwald ripening to occur, we need to have fluctuating temperature. It can't just be a continuous pattern of cooling. Now, there are some interesting features we find in the Shap Granite. This is an example of one. We've looked at this in a previous lesson. This is an enclave. What do you think's happened here? What does that tell us about the cooling history of the Shap Granite? What was this material like when it was incorporated into the granite? Was it a lump of cold country rock that's fallen into the granite? Or is it an input of new magma? And with new magma comes a rejuvenation of the magma chamber. More heat, more volatiles going in. What do you think is going on? Okay, as we look out from Shap Summit, let's think about what we've come across here. We've got a rock that you've all seen before, and that you may have comfortable interpretations of. Yet, that rock, if we apply our new ideas from this topic, can't have formed in the straightforward way that we've thought of so far. Clearly, the evolution of magma is a more complicated picture than just one blob of molten material cooling gradually over time to produce the rock that we see. It shows us how important it is to actually really understand Bowen's reaction series and how much it tells us about how igneous rocks form. Next time, we need to look at phase diagrams in a lot more detail and try to get our heads around how they work. I'll see you then.